Aloha. Welcome to our community service series in How Computers Work. I'm Elder Stanley, a missionary for the Church of Jesus Christ of Latter-day Saints.
Hi, I'm Austin Kellum. I'm a student of Elder Stanley here.
This time we're discussing how computers use digital logic, how the logic works that makes a computer work. It turns out that all of the logic inside of a computer is accomplished through three fundamental logic gates. Those logic gates are an AND, an OR, and a NOT. Those logic gates make possible any logic circuit. The AND gate, you can see here, we require two switches to be closed for an AND. This is like Mom says, you must clean your room and you must do your homework and then you can play your computer. An OR is a parallel switch. You can close this one or this one. That one says something like you can take your pick. You can either do your homework or you can clean your room. Either case, you can play your game. The NOT is the opposite. If a yes comes into a NOT, a no comes out, or a 1 goes in, 0 goes out. It's the opposite of what goes in. Let's try these little logic gates for just a minute and we'll see how this works. Over here, this is a tool that we'll be working with throughout this series. But anyway, this is a tool that lets us play with ANDs, ORs, and NOTs. So here's a 0 comes into an AND. If we want to make an output 1, we have to have that one and we have to have that one. Then the output's a 1. With the OR circuit, we could press that one, or we can press that one, or we can press both. Here's a NOT circuit. In the NOT circuit, if a 0 goes in, 1 comes out. 1 goes in, 0 comes out. I don't know if you've ever done this, Austin, but when I was a kid, sometimes Mom would say, "Have you done your homework?" And you'd say, "Sure, Mom, I've done my homework." Not. Anyway, or cross your fingers or some kind of thing. Anyway, that's a NOT circuit. And we'll see that with those AND, OR, and NOT, we can build all kinds of things. So let's come back to this PowerPoint presentation. If we look at this next one, this is an example of how we can use AND, ORs, and NOTs to build another circuit. This circuit's called an exclusive OR gate. What the exclusive OR gate says is like you can have cake or you can have cookies, but you can't have cake and cookies. So that's called exclusive OR, and you can see the exclusive OR is made up of a NOT, a couple of NOTs, a couple of ANDs, and an OR. So we can use other elements to build more complex elements. Let's look at this one in our logic simulation just for fun. So here's an exclusive OR gate made from ANDs, ORs, and NOTs. We can see if we have 1, 1 come in, then 1, 1 goes out. If a 1 comes in here, a 1 goes out. But if we've got 2 1s coming in, a 0 goes out. 2 zeros come in, a 0 comes out. This is the circuit that we would make out of ANDs, ORs, and NOTs. In our logic simulation program, we can get a single gate that does all of that. That's called an exclusive OR gate, rather than a components of an exclusive OR gate. We'll see later on that we can use an exclusive OR gate to flip bits. If a 1 comes in here, what comes in here is flipped, goes out. If a 0 is here, it doesn't get flipped. We'll see later how we could use that to make an encryptor-decryptor circuit. The logic simulation circuit that we're using is one called Logisim. It's free software. It can be downloaded from sourceforge.net. It allows you to experiment with digital circuits from transistors to complex circuits. It was created by a guy named Carl Birch, and I really appreciate Carl for making this software, which I think is excellent software, available for free. Last time you asked about how transistors worked. We're going to see that transistors are the switches that let us build ANDs, ORs, and NOTs, and then even more complex logic circuits. What we need to have to build logic circuits is a switch. We want a switch that can switch fast. In this case, we have transistors. These are called MOS transistors. MOS stands for metal, the gate part, an oxide layer in here, silicon dioxide, very good insulator, and then silicon below that. And so it turns out we put a voltage on the gate and no current flows, it's just a voltage because it's on an insulator. And then we have a source and a drain, so we will control current flow from the source to the drain by applying a voltage to the channel. We have those in two versions, N channel and P channel. N channel, we make silicon either positive or negative, so it either has extra electrons or extra holes by putting some dopants in the silicon. You can see here in this little subset of the periodic table that I've got here on the screen that phosphorus has more electrons than silicon, and arsenic. Silicon has just enough electrons so that everything is just tightly bound up. But if I put in a little bit of phosphorus in with silicon, then there'll be extra electrons. If I put in something like aluminum or gallium or boron, there'll be less electrons. So if we have some silicon that's, they call it doped with a little bit of boron, for example, then it will be P-type silicon. If we have a little bit of arsenic, then it'll be N-type silicon. And so those will make these regions that define our transistors. Here we've made this so there's extra electrons in this part, and we want to form a channel with positive charge carriers between here. The way we do that is we apply a negative voltage to the surface, and that pulls positive charge carriers up here, and we form a channel. In the case of the N-channel transistor, we apply a positive voltage. We pull electrons to the surface and form a negative channel from the source to the drain. Anyway, that's kind of how transistors work. Really fast, brief explanation of a transistor. This shows these transistors that we're going to see in our logic simulation. We have P-channel transistor, has a little circle there. That means we've got holes. The electron in the N-channel transistor, we don't have that hole. Anyway, current will flow from the source to the drain depending on the voltage that's applied to the gate. For the P-channel device, we put a negative voltage on the gate, the source and drain are connected. When we have an N-channel device, we apply a positive voltage to the gate, and the source and drain are connected. So we can turn the transistor on and off by applying a voltage to the gate. Let's look and see how we use those transistors to build one of our fundamental logic gates, in this case the inverter. When the input is 0 in this inverter circuit, 0 comes in, the P-channel transistor is turned on, and the output is hooked to the high voltage, which is a 1. So 0 goes in, 1 comes out. If we put a 1 in, the P-channel transistor turns off and the N-channel transistor turns on, and so now the output is 0. If a 1 goes in, 0 comes out. Let's see how these transistors work in our logic simulation. Here's our inverter circuit. So in our inverter circuit, you can see a P-channel transistor up here. Right now we've got a 0 coming in, so a 1 is coming out. If we change that, so we have a 1 going in, now the N-channel transistor is turned on and the output is pulled low. So this inverter works by having two transistors, only one's on at a time. If we have a 1 coming in, just the N-channel transistor is on. If we have a 0 coming in, just the P-channel transistor is on. So the output is opposite what the input is. It turns out in the real world of silicon manufacturing, it's a lot easier to build what we call inverted gates, a NAND gate. A NAND gate is like an AND gate followed by a NOT, or NOR gate is like an OR gate followed by a NOT. When we actually implement these, you'll see why manufacturers would prefer to build NANDs and NORs rather than ANDs and ORs and NOTs. But it turns out we have one of those we can actually build any circuit, either a NAND or a NOR. We can build anything. This shows what those look like. You can see that the NOR gate is the fundamental thing we build. If we want to make an OR gate, we put an inverter after the NOR gate. So that's why manufacturers prefer to build either a NOR or a NAND. If they don't need this inverter, then it's simpler. If they have to have a AND, they'll use the inverter, but a lot of times they don't. A NAND will really work. Same thing with a NOR. So these are an OR from a NOR and a NOT. So you can see it works just like the OR circuit that we looked at earlier. We can turn this one on, one will come out. We can turn this one on, one will come out, or we can turn them both on, one will come out. Here's the AND. And the AND, we have to turn this one on, and we have to turn this one on for one to come out. This is an example of a really important circuit that we use all the time in computers. This is how we make a memory element. You know, computers have all kinds of memory. I guess your computer at home has got what? Like something like 30 gigs of random access memory or something like that.
Yeah.
Anyway, memory is really, really, really important. This shows how we can again use ANDs. In fact, these are NANDs and a NOT circuit, and we can build something that's called a data latch. This is stores 1 bit of information. We need to use lots of storage inside of a computer, so this is a really important circuit for our computers. Let's go over and play with this one and we'll see how it works. Okay, this is a memory cell. Notice it's got 2 kinds of inputs. This is a data input. What comes out doesn't depend on that, but what comes out, you have to write data to it. So it was read when it didn't have anything stored, but now it's got a 1 stored. Doesn't matter what this is out here. If we write when there's a 0 out there, we'll store that 0. And then it doesn't matter what's coming in here. A 0 is stored. We can write whatever. It stays there until we write something different. If we got a 1 there and we write, stays a 1. So anyway, that's a memory cell. Key part of any kind of a computer we try to build. The next thing I wanted to show you is how we have math, how we can do math with digital logic. We talked about one of the things that's really kind of nice about binary is the math is a lot simpler. This is showing our addition facts in binary. So if we have 0 plus 0 plus 0 is 0. If we have 0 plus 1, we get a 1. If we have 1 plus 1, we've got 1, 0. We saw that when we talked about there's that many kinds of people in the world, those that appreciate binary and those that don't. Anyway, that's a 2. And if we have 1 plus 1 plus 1, we've got 1, carry 1. So in these 2 cases, we have a carry to the next column. And so what we need is a logic circuit that can take an A input, a B input, and if we're talking about a column that's over in our addition, we need to be able to have a carry in. And so this is a circuit that will do that binary math with digital logic. Let's go over and look at this circuit for just a minute. So this is what this looks like. If we have A come in, then the sum bit is 1. There's no carry. If we have 2 1s come in, the sum is 0, but the carry out is 1. And then if we have 3 1s come in, now the sum is 1 and the carry out is 1. Notice this is a circuit with just ANDs and ORs and NOTs, and it can add 1 binary bit. But just adding 1 binary bit's not very satisfying. We really want to have big numbers, right? Like your computer's a 64-bit computer, you want to be able to add 64-bit numbers. This shows how we can take these adders and combine them to get bigger numbers. So, here's the main circuit. So this is a 4-bit adder. Each one of these is one of those 1-bit adders. It has an A input, a B input, and a carry in input. And then coming out is a sum output and a carry out output. And so what we do when we add a binary number, We can maybe put this one on our whiteboard and have you work one out. But let's try a number like, let's try 1, oh shoot, let's turn this on. 1, 1, 1, 0, and then we'll add 1, 1. So what would this number be in binary? So we got 8 plus 4, 12. So this is 14 plus 8 and 12. That should be
That's 12.
that. But anyway, trust me, go ahead and put this binary number in your binary computer calculator or work it out on a whiteboard. You'll see that this is how we can add 4 numbers and get an answer with just ands, ors, and nots. So here's our 4-bit adder. There's another circuit that we use a lot inside of computers. This is called a decoder. What a decoder does is takes a binary number and converts it into into what its value is. So if the binary number that comes in is 1, we'll light up 1. If a 2 goes in, we'll have 2 light up. If a 3, the binary number represents 3, we'll see 3 light up. If 0 goes in, we'll see 0 light up. These are the parts that make up that decoder. This is what it would look like if we used one that's built into our library of circuits. So what happens in this circuit, we put in a number. Right now the number that's in here is 1, 1. That's a binary 3. So 3 is coming out. If we put just zeros in here, 0 plus 0 is 0, or 0, 0 is 0. If we put a 1 in here, that's a 2. If we put a 1 in there, that's a 1. And so we see how we can use ands and nots, and we can take in a binary number and decode it to a binary output. We'll use this when we look at our full computer later on. We use this one to figure out what kind of operation the computer's doing. We'll have 4 operations, and we'll have a number, and we need to figure out whether that instruction's an add or a store or a load, and we'll use a decoder to do that. This next circuit is called a selector. The selector actually has a decoder built into it, but then it uses that decoder to select one of, in this case, if it's a 2-bit selector, it will select one of 4 inputs, one of 4 inputs, and we'll select one of those by the number that goes into the selector. So right now, what's selected is 0, 0. So that means, 3 changes out here, doesn't do anything. 2 changes, doesn't do anything. The only one that's selected right now is a 0. And if the 0 changes, the output changes based on that input. If we select down here 3, then if the 3 input changes, the output changes. Here's one that I think you enjoyed last time we played with that, Ryan.
Yes.
This is one that's using an exclusive OR gate that we talked about, where we can use the exclusive OR gates to flip bits. In this case, we'll take some bits from something that we type and display that, and we'll flip some of the bits and it'll scramble our text. But then if we send that scrambled text back through another inverter with the same string, it will unscramble it. Whatever bit got flipped up here will get unflipped down here. It's called symmetric encryption decryption. Okay, so in this case, if we type something on the keyboard, but we haven't, okay, so we're typing text up here, this is a test. We're not flipping any of the bits, so the encrypted looks just like the decrypted. So now we're typing hello world up here, and what you're seeing down here is something that's really scrambled. But we take that scrambled text and we apply the same decryption key to it, and we get a text that's the same text we type in. So with an exclusive OR, we can encrypt and we can decrypt text. Let's go back to our PowerPoint and see where we're at. We're getting close to the end of our presentation here. Next time we're going to use this logic that we've talked about today to build a computer processor, a CPU. We'll see how a CPU needs to have storage, needs to have a calculation capability, it needs to have decoders, needs to have selectors, It's got a lot of components, but we'll look at a simpler computer. We'll see how all these logic gates can be combined to build a CPU. Excited about that?
Yeah.
Okay, good.
Learning about the brain of the computer.
Yeah. I guess this is not nearly as complex as the one in the computer you got at home. But you have an i7 at home, right?
Yeah, pretty expensive.
Yeah, yeah. Anyway, this is going to be a really simple processor, not nearly as complex as your i7, but it shows the principles. The i7 processor has billions of transistors. This one has just a few hundred. So,
yeah.
Anyway, see you next time.
See ya.